Hello.
Hello, how are you?
Tired, but doing well.
Doing well, that's good, that's good. I saw the notes you sent. Thank you.
Yeah, it's
Hello,
called.
hello. Yeah, see. So, let me join iPad.
Recording in progress.
See. Okay. So I see that you went over oxidation by periodic acid with HiO4.
Yeah.
So that reaction is going to cleave vicinal diols,
Mhm.
oxidation by periodic acid, which is HiO4. That's going to cleave vicinal diols. So we could have two alcohols that are vicinal or adjacent to each other. Um, so the example that he gave is this molecule here, where we have two alcohols, 1, 2, that are vicinal or adjacent to each other, like that. And when we
Mhm.
react this with periodic acid HiO4, that's going to cleave that bond that is between those two carbons holding the alcohol and oxidize the carbons into carbonyls, right? So this carbon here is going to have a carbonyl with that oxygen, where that oxygen is that oxygen of the alcohol right there,
Mhm.
right? And that's going to be the same for this carbon right there. Right? And the example that he gave below is a sugar, where when we react the sugar with HiO4, we're going to cleave the bond between the vicinal diol. So we have two alcohols here, one here, two here. So we're gonna cleave this bond between the two carbons holding those two alcohols to give us this product here. Right. So I'm gonna color code these carbons holding alcohols in blue, which are these carbons right here, where those carbons right there are going to be the ones with the carbonyl. Right. So a carbonyl there and carbonyl there, like that. And we see that these blue carbons here also have hydrogens. So these carbonyls here are specifically aldehydes, right? So you could draw out that hydrogen explicitly out like that to show those aldehyde functional groups in those product like that, in that product like that. Right. Okay. The side products would be iodic acid, which is HiO3 and water, H2O. Okay. So the mechanism of this is going to be a little bit weird because there's heterocyclic arrows. So here's the mechanism. Here's the vicinal diol, the adjacent alcohols. reacting with IO4 minus in water, that's going to lead to this intermediate here. He didn't show how to get this intermediate, but he showed this intermediate.
Yeah.
We could color code what those atoms are. Or these carbons here of the vicinodiol in blue, or these carbons here in blue. And the IO4 minus is going to be this IO4, 4 oxygens.
Uh,
1, 2, 3. Whoa, wait. 1, 2, 3. 1, 2, 3, 4, 5. Okay, so one oxygen of the O4 is gonna get kicked out somewhere in the mechanism, because that purple IO4 is gonna be this part of the intermediate right here, right? Where one oxygen is gonna get kicked out as a leaving group, because these oxygens of the alcohol right here in yellow are gonna be these oxygens right here in yellow.
yeah.
Okay. And then from here, he didn't show the well, I guess he did. Like the arrows to cleave those bonds are going to be like this. This bond that we're interested in, that's going to get cleaved or broken, is going to make a double bond right here, which is going to form that carbonyl. That's going to make that's going to kick out this iodine. So that bond right there with 2 electrons are going to go into the iodine, and we're gonna break this bond and form a carbonyl right there, a double bond right there, which is going to give us
The carbonyl.
the carbonyl here and there with the IO3 minus leaving group, iodic acid. Right. Like that. Okay. And we can like just draw out the R groups that these blue carbons always had, which are these R groups right there. Right. And if you want to keep track of the atoms again, these carbons here are the blue carbons. These oxygens here are the alcohol oxygens, and this is the purple IO4 minus right here, like that. Okay. Yep. Any questions on this reaction or mechanism?
Not really. No.
Okay.
Wait,
Okay.
wait. Is there a reason
Uh-huh.
why it stops at the aldehyde for the example?
Oh, like why it stops at the aldehyde right here?
Yeah. Why doesn't it become like a carboxylic acid or something?
Yeah, it doesn't go all the way to a carboxylic acid because this is not a strong enough oxidizing agent to do that. Something that would be strong enough that would go all the way to a carboxylic acid is KMNO4. Right. So if you see KMNO4, this would be a strong oxidizing agent that would be able to oxidize the intermediate all the way to a carboxylic acid. It would not stop at the aldehyde. It would go all the way to the carboxylic acid. Strong oxidizing agent. This HIO4 here is still an oxidizing agent, but it's not strong enough to go all the way to the carboxylic acid. It stops at the aldehyde.
Oh, okay, okay.
Yeah. Okay. Okay. Let's see. Yeah, so there were like 3 major topics that you went over in this lecture, which is the oxidation by periodic acid, thiols, and like the properties of thiols, and then the ethers, like the
Yeah.
ethers.
Just the properties of ethers.
Yeah, properties of ethers. Right. Okay. Were there any questions that you had like specifically about those topics, or
Uh,
struggling with?
let's see.
Mhm.
Can you go over the oxidation of thiols?
Yep, oxidation of
Yeah.
thiols. Let's do that.
From the sulfinic to the sulfonic.
Yeah. Sulfonate to sulfonic. Oxidation of thiols. I see. Okay. Sulfonic to sulfonic. Oh, the second line of the oxidation.
Yeah.
Right.
Or is it
So
two oxidants?
this is a thiol right here. It's similar to an alcohol, right? Where the heteroatom atom here, instead of an oxygen, is going to be sulfur. And sulfur is on the same column as oxygen, same group as oxygen. So it's one like energy shell bigger than oxygen. When we think about oxidation and reduction, we can think of oxidation as the gain of bonds to electronegative atom, like oxygen, sulfur, or nitrogen, and reduction as the gain of bonds to hydrogen, right? Or you can think about it as the reverse. Like oxidation is the loss of bonds to hydrogen, and reduction is the loss of bonds to electronegative atoms. So when we are going to oxidize this thiol here, we want to add bonds to electronegative atoms. So when we use some kind of oxidant, aka oxidizing agent, like hydrogen peroxide, H2O2, we're going to oxidize that thiol into a sulfonic acid. Sulfonic acid. Where if we focus on this sulfur atom right here, this sulfur atom had 0 bonds to oxygen and 1 bond to hydrogen. But when we oxidized it, we gave it 3 bonds to oxygen, and now it has 0 bonds to hydrogen. This is not the most oxidized form of this sulfur atom because we can even add more electronegative atoms. If we add a stronger oxidizing agent or oxidant, that's going to oxidize that sulfur atom even more into sulfonic acid. Where this sulfur atom here now has 1, 2, 3, 4, 5 bonds to oxygen, which is even more bonds to an electronegative atom. Sulfonic acid, right? He didn't give an example of a strong oxidizing agent or oxidant that would give this reaction, but
For the H2O2, he just said that's just an example of one oxidant, but he didn't
yeah,
list any.
H2O2 is an example of an oxidant that would do this oxidizing reaction. Did he give any examples for this oxidant?
No, he just said I think it's the same one, but it has to be like stronger or something.
Oh, okay. Same one was stronger, right? So the concept is still there. Oxidation is going to give this sulfur atom more bonds to electronegative atoms. You can think of it like that, right? Okay. Yep. And if you look at the top line, would we have that thiol and we put some kind of oxidant or oxidizing agent to it, we could oxidize this into a disulfide, which is still an oxidized form of this blue sulfur, because this blue sulfur now has 1 bond to an electronegative atom, which is sulfur, and 0 bonds to hydrogen. Right? Before it had 0 bonds to an electronegative atom and 1 bond to hydrogen. So oxidizing, we're adding a bond to this electronegative atom and removing this bond to hydrogen right there. So this is another example of an oxidation reaction here.
Right? Okay, that makes sense.
Yep. Okay. Did you have any problems with the ethers, functional groups, or properties?
No.
Yeah. That's more.
He explained it pretty well.
Yeah, that's good. That's good. And it's like a lot of like Gen Chem concepts, like the dipole, H bonds. That's good. Okay. Yeah. Did Bill post any practice problems yet for the midterms or not yet? He's still
he posted the practice midterm, but we haven't learned everything. So
okay, yeah. So we'll probably save that for later.
Yeah.
But you could send me it soon, so then I could like look over it and
Okay.
see
Yeah.
what his problems are like, and then start like creating similar problems to his problems. Yeah. Okay. Hey, Elysia, how are you today?
Hi, can you hear me?
Yes, I can hear you.
I'm doing okay. I was like kind of I was stuck on the problem that you gave me last for
Oh,
homework.
right. The homework I give you. Did you
Yeah,
try it
also,
or
yeah, I did.
yeah.
I'm not sure if you gave me H2SO4 with CH3OH, but I kind of assumed that you did.
Yes.
Um,
Let me copy these. Okay. For which problem did you assume that for?
um, is the where is it? Is the for D or it was
D.
sorry,
Right.
the very last one
Oh,
or
yes.
A
A.
or yeah, D, sorry.
Yes. D.
That
Right.
one, yeah.
Yeah. So there is H2SO4 there.
Yeah, so okay, good.
Mhm.
Um, but no CH3OH.
No C3OH, no
Okay.
H2O, just H2SO4.
Okay, so what I started off was I grabbed the alkene and attacked the hydrogen, and that hydrogen bond between the SO4H broke off, and
Mhm.
then um, there would be a carbocation. Oh, also, the bond at the end of the alkene was what was gonna attack it. That way we can form the carbocation
Mhm.
um, there, but then there would be a hydride shift because we want the carbocation to be in the more substituted position. And then I think afterwards, I assumed that I would form that ring. But the
Yes.
thing is,
So,
like, that would make a five
uh-huh.
membered ring.
Yes, you're correct. This oxygen atom here is going to attack that carbon to form a 1, 2, 3, 4, 5 membered ring. But once we form this carbocation intermediate here after protonating this alkene, there's no hydride shift or methyl shift to worry about here because it's already at its most stable position, most substituted position.
Okay.
Right. Okay. So when we make that 5 membered ring, oxygen is part of that ring. So when we draw that template out, we can say that's 1, 2, 3, 4, 5, like that. And what can we do from here?
And then we add on the fluff.
Yes, we add all the fluff, which at carbon 2, there's a methyl.
Yeah.
Carbon,
And then we would have
mhm,
for 5 there would be the methyl and the ethyl, right? Or no,
yep,
yeah.
methyl and ethyl.
And then the H from
Yes, on the O, and giving this O a formal charge of
plus.
plus. Right. We're almost done with this mechanism here.
And then we would have um the the H2SO4 that came in, but it's an
Uh-huh. You could use
HSO4 minus.
HSO4 minus, right, as a conjugate base.
Yeah, and that would come in and um,
Mhm.
grab the carbocation and then make it neutral. And then
Yes,
that
it
bond would,
would
yeah, kick it
grab
off
the
to
hydrogen.
oxygen.
Yeah, and
Yeah.
then that bond would go onto the oxygen, neutralizing that carbocation, making it
Yes.
neutral. Yes, like that.
Oh, okay, so
Giving
then I
this.
did get it right.
Yes, yes, nice.
Yay.
Yay. The Helix, he really loves intermolecular reactions. Like a lot of his exams has some sort of ring to it. Like
Mm-hmm.
forming a ring or breaking up a ring in his exams. So that's good.
Oh.
Uh-huh.
Okay, yeah, I was kind of confused because I didn't, I was kind of assuming that you gave me CH3OH, and then I
Mhm.
was like, oh, there's CH3OH, but then there's an OH, but CH3OH is preferable over OH. So then that kind of was, even though it wasn't there, I kind of was thinking
Mhm.
whether or not. But then I know, like, I think rings
Mhm.
are more,
More
even
favorable.
more, yeah, more favorable.
Right, because even if there was CH3OH here as a potential nucleophile, this would be an intermolecular reaction if the alcohol of the CH3OH attacks the carbocation, because the nucleophile is separate than the electrophile. That's an intermolecular reaction.
Right.
But in OChem, intramolecular reactions are way faster than intermolecular reactions.
Right.
So even if there were CH3OH or CH3CH2OH, that would be the minor product. The major product would still be this, where it results from the intramolecular reaction.
Right. So that's also what I was thinking.
Yeah, that's good.
Yay.
Yes. um, did you finish the other homework parts that I gave you last night?
Yeah.
Mhm.
I should have forwarded it to you, but I was like kind of stuck on that one.
Uh-huh.
So, here, let me export this.
Yeah. Explain it to me. Hey Jenna, how are you?
Hi, I'm good. How are you?
I'm doing fine. You're from Chem 8B, right? For Levens?
Yes, I am.
Yes. How's that class going so far for you?
So, it's going okay. I had way for 118A and it was really difficult. So I went into 8B
Uh-huh.
thinking like I wouldn't really have a good foundation, but
Uh-huh.
because a lot of the stuff that we did at the end of 118A
Mhm.
is being introduced this quarter, I
Very-
feel like it's a easier transition.
Yeah, because the 8 series and the 118 series, they have a different order of
Yeah,
how they teach things. Right now you're learning about alcohols, right? I think at the beginning of
yeah, it's
118.
not too bad. Yeah,
Yeah, that's good. And Wei was last quarter, right? Fall? No, not fall
yeah,
quarter.
yeah.
Wait, fall quarter, fall quarter. Yes, yes,
Fall
yes.
quarter, yeah.
Yeah, I heard she was like pretty hard. Like you didn't know what to expect on the exams.
Yeah, it was so many curveballs.
How many curveballs they
Yeah.
right. Um, were there like any problems or topics that you wanted to go over for 8B? Like, do you have your first quiz soon? Is it this week or is it next week?
Yeah,
Evens?
it's on Friday. It's
It's on
gonna be
Friday.
on alcohols and a little bit on ethers. I
Uh,
was struggling with the nomenclature of ethers.
Nomenclature of ethers. Yeah, so I have to like brush up on my nomenclature rules as well.
Mm-hmm.
So can you send me what you have so far? Like the practice
Yeah.
problems and the notes through like my email.
Okay. What's your email?
Yeah, yeah. Let me type it in the chat.
Okay.
You could either send it to the email or school. Like I think school allows you to send files,
Okay.
or even here on the Zoom chat. Like the Zoom chat like allows you to add files as well.
Files? Okay.
Yeah,
I'll put it on here.
yeah, yeah. Okay. Yeah. Okay. So what we'll do is we'll check Elisa's work for the um, homework. Let me import that to the document, and then we'll do some practice for the quiz this Friday for 8B.
Okay, sounds good.
Yeah.
Oh, also, Brian,
Yeah.
I forgot which ones, um, I know one of the ones I have there, we worked on together, I think it was 3A, but I didn't complete it, or I didn't get write the rest down
Mm-hmm.
onto
Yeah.
that
So
one, but I forgot which ones that we
yeah,
went into.
for that one, you could walk me through that and explain to me in words what you would do there.
Like from review, like last time.
Yes, like when I
Okay.
like review these with you, and then we get to this point here where it's not finished, you could explain to me what would happen next, or if you get stuck, let me know so I can walk you through it. We could walk through it together.
Okay. So are we going over 3A? Okay.
Yeah, let's go over 3A.
Okay. So we have um that, and then we have the carbocation
Mm-hmm.
after reacting with H2SO4, and then I think this is the part where we have our or water come in because
Mhm.
it's more preferred compared
Mhm.
to like H2SO4 because there's millions of them.
Yes, and also there's an
And it's
excess amount of
better
H2O and there's
base.
excess amount of acid as well. So they're actually pretty equal in equivalence,
Oh,
right?
okay.
But there is another reason why H2O is more preferred over, let's say, HSO4 minus. And I'm gonna draw the HSO4 minus in this form, and I want you to find a reason why, let's say, this water here is a stronger nucleophile than this HSO4 minus. Like, why is this oxygen atom a better nucleophile than this oxygen atom here?
Um,
Think about which oxygen atom is more stable. Which pair of electrons is more stable? Let's say we were focused on this pair of electrons versus this pair of electrons. Which one is more stable and why?
I think the H2SO4 is more stable.
HSO4 minus is more stable because it could do
Resonance.
resonance, right? And if it's stable, it could do resonance. It's happy, which would make it less reactive, less energy.
Right.
Right. So because it's so stable, it's happy. It doesn't want to react. It's happy by itself. It's like not going to do anything. Whereas water here, that pair of electrons is stuck. It's suffocated there. There's no like there's less breathing space for that oxygen, and because
Right.
it is less happy, it's angry. It's going to be more reactive. Right.
Right.
So that's why water there is the stronger nucleophile than the HSO4 minus, which is going to attack that carbocation right there.
Right.
Right. Mhm.
And then I think that one is going to attach, and then we're gonna need to have another water come in
Mhm.
to make it neutral.
Yes. And for the mechanism, Helix doesn't really care which one you use. You could use water as a base, or you could use HSO4 minus as the base to regenerate the acid catalyst. But Helix, he doesn't really care. You could use water as well, um, which would deprotonate that positive charge oxygen to make it neutral alcohol like that.
Yes.
Yes, you got it. Yeah. So that will be the final product for 3A.
Right.
Nice.
And then the rest of them I actually did complete. So
So let me check. Let me check it. Like, it's so neat. What the
thank
heck?
you.
Yeah. H2 PDC Sin edition. Oh yes, yes, and you included the other version as well. Enantiomer. That's good. Um, oh, okay. Let me see here. Let me see if these are actually enantiomers, because I see that you reversed the ethyl and methyl groups spot, and that might mess up the chiral center. Let's say this is the red chiral center, which is that red chiral center right there with the ethyl group. And say this is the blue chiral center, which is that blue chiral center right there. The R and S for this, let's say this is gonna be uh, 1, 2, 3. Going this way, it looks R, but it's actually gonna be S because hydrogen is on the front side. For blue, that's gonna be 1, 2, 3. So it looks S, but it's actually R. Okay, let's look at this red one here. This is 1, 2, 3. So this is S, and it stays S because hydrogen is on the backside. And for blue, that's going to be 1, 2, 3, R, and it stays R because hydrogen is on the backside. So right now, we have to be careful here because we see that the red chiral center stays the same as S. The blue chiral center stays the same as R. So what you drew here is the rotated or flipped version of this molecule. Like if you imagine a model kit of this molecule, if you flip it upside down like a hamburger, that's going to result in this molecule here. So these are identical molecules here.
Oh, okay.
Right. So to be safe, when you draw the enantiomer of it, make sure you are consistent with the R groups as well.
Okay.
Right. Mhm. Okay. Um,
So then how would you adjust
mhm.
that one?
Yes. To adjust this one, I would draw my ethyl group up here, methyl group down here, and hydrogens would be right there. It doesn't matter where the hydrogens are because they're the last priority group. So you could draw it like right here, right here, or right here. It doesn't matter because the fourth priority group like doesn't assign RNS. You could say the most important ones are 1, 2, and 3. The fourth lowest priority group could be in any direction, but the fourth priority group is actually very important because we want the last priority group to be on the backside, the dash. Like if we saw in this example here, we saw that it wasn't in the backside, so we had to flip what it looked like, right?
Right.
So then that would make, like, let's say this is the red car center because that has the ethyl group. This is the blue car center right here. This would be 1, 2, 3 for the red car center, and that would be clockwise, which is R, and it stays R because the lowest priority group is on the backside. So that's R for the red. For blue, this is 1, this is 2, and this is 3. Going this way, it looks S and it stays S because the lowest priority group is on the backside. So blue here would be S and it stays S. Now, these two here would now be enantiomers of each other because every chiral center changes. So your two answers here would be this and this right here, right? And we know that these are enantiomers of each other because there are no other existing chiral centers. Like there's nothing like that, right? So we know those are enantiomers. So just to save time, you could have also just done that symbol as well to show like the plus enantiomer version is that. But that won't work all the time because you might have a pre-existing chiral center like that, which you cannot use that symbol anymore.
Right.
Right. Yeah, because this molecule here is the same thing as this molecule that you drew right here. They're identical.
Okay, thank you.
Yeah. Okay. For the next one, 2A. 2A. Yes, we protonated the alkene to form this flat and planar carbocation, sp2 carbon. So when the CO minus attacks that carbon, it could attack on either side. And this won't be hydrogen here. It would be the chlorine that attacked that carbon.
Okay.
Right, like that. But you got the stereochemistry correct, and that is good. That's correct, like that. Okay.
Oh, okay.
Yep. Because the chlorine atom here is attacking that carbon, which is making that new bond right there. And
Right.
it could be wedge or dash because it's flat and planar. Yeah.
Oh, okay. Oops.
Yep. Okay. Like on the top side or bottom side. That's good. Okay. This one, protonate alkene from carbocation, hydride shift. That's good. From the more stable carbocation, Br minus attacks that carbon. And based on the last problem we did, what would the final product look like here when the bromine attacks this flat and planar carbon?
Oh, there would be the wedge and dash.
Wedge and dash. Let's say bromine is here. If you choose this to be wedge, this ethyl would be dash. And since there's no chiral center here, we could actually just leave it as flat and planar because we only put wedges and dashes for chiral centers.
Oh, okay.
Right. This is not a chiral center because this group is the same exact group as that group right there. So that's not a chiral center.
Okay. Yeah, I think I just forgot to add the bromine there.
Yeah, it's okay. It's okay. 3A, we did that. 3B, protonate alkene, form a carbocation here. Methanol attacks. OCH3. Yes, so the final product here is correct, but when we think about the mechanism here, the second equivalent of methanol here, what it's going to do, it's going to grab this hydrogen, the bond between that hydrogen and oxygen is going to break
Oh,
and go onto the
oops,
oxygen
yeah.
right there because we want to get rid of that positive charge right there.
Yeah, okay. I
Right.
think that was yeah.
Yeah. And in this case, we did not have to include stereochemistry, wedge and Nash, because this is not a chiral center. Right.
Right.
If this was a chiral center, then you would have to put like a wedge, and the other one would have to be a dash. And then if there's no other chiral center, you could put the symbol to show the enantiomer
Right.
version of it. Okay. For the 3C, right? Carbocation 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2 ethyl, and then 5 2 methyls. And then for this last part here, there's one thing missing in this intermediate. What is that one thing missing here?
Oh, the plus.
Yes, positive charge. Formal charge of
Yeah.
+1, because this oxygen has 3 bonds and 1 pair of electrons.
Right.
Uh-huh.
And Helix always emphasizes like that you really should put the plus there. So
Yes,
I forgot.
that is very important for mechanism, especially.
Yeah.
And this is the final product with the ethyl. But how can we get rid of this plus charge and hydrogen here?
We have another it's the HSO4 minus, right?
Yes, the HSO4 minus that we formed at the first step. Like once we
Yeah.
protonate the alkene here, the HSO4 minus gets formed, which is going to be reused, or which is going to be used in the last step to reform or regenerate this acid catalyst here.
Right.
Mhm.
Okay.
Yeah. Grab that hydrogen, bond between that hydrogen and oxygen, goes onto that oxygen to give us this final answer there, final product there.
Okay.
Okay, and then 3D, this one, protonate. Oh, so for this one here, where would the carbocation want to be at? The more sub or less sub carbon?
The um the the carbocation wants to be on the more sub.
Yep, the more sub carbon. So in this case, which carbon would be protonated?
It would be the one on the bottom.
Yes, this one.
Yeah.
Uh-huh.
I
This
think
one.
yeah, that was the part where I actually had the alkene bond attached to the other bond right there, and then I like before I sent it to you, that's where I had the arrow drawn from so that the bond that the alkene was on the last carbon.
On the last
I
carbon.
just forgot to adjust the arrow.
The alkene is right
Yeah.
here.
Yeah,
As
because that's why I
oh,
actually drew that hydride shift, the
yeah,
one
yeah,
on the one next to it. That's
yeah.
why yeah,
Yeah, yeah.
I wrote the bonds wrong, but
Oh, yeah. That's good. That's good. I was like, the this is not good. This is not correct.
yeah.
Like this one, 3D, 3A. Yeah, because once we have this alkene right here, we want to directly go for the more substituted position. I, we don't want to like form the less stable carbocation and then do hydride shift later on, because that's more work for the molecule. The molecule would want
Yeah.
to get to the most stable carbocation with the least steps as possible.
Yeah, what's weird was like I copied it down from
Uh-huh.
the last meeting like that. So I kind of drew it like that, and I thought that you were trying to trick me and have me do hydride shift,
Oh,
but there
yeah.
was no hydride shift. So
Yeah.
yeah,
If the alkene was here, no hydride shift. Right. But
yeah.
if
But
the alkene is
I
like
know it has
this,
to be on the more substituted. So
yes,
that's
then we
kind of
want
why I thought that way.
to. Yeah. That's good.
Yeah.
Okay, hydride shift. And uh, this is intramolecular reaction where this oxygen would attack that carbon, forming a 1, 2, 3, 4, 5 membered ring. We don't go to 6 because that carbon there is not involved in the ring at all, right? It's
Yeah.
not part of the ring. So we don't number 6 there. 5 membered ring. 1, 2, 3, 4, 5. Good. 1 is oxygen. 2 has the methyl. 5 has the ethyl. Wait, we did this one.
Yeah.
Wait, what?
I think like when we were going over it together,
Uh-huh.
um I kind of that was my work, but I left it at the numbering that I had it because from the very start, I
Uh-huh.
had the alkene attached to the last one. So
Uh-huh.
that's why I numbered it that way.
Oh, numbered it this way. I see.
Yeah,
Yeah.
but after,
Mhm.
yeah,
Like getting the intermediate,
yeah,
you know that you stop at the electrophile,
yeah,
and then you don't go further than that because this is
yeah,
considered a decoration on carbon 5,
yeah.
which is this one here. Yeah, that's good. Nice. Let's see.
It's not so bad.
That's good. Yeah, it's just a lot of like small details with the positive charge, the hydride methyl shifts, and especially this part right here, like deprotonating the positive charge oxygen with the second equivalent base or
Yeah,
HSO minus. Yeah, that and also the chiral centers as well. And like if it's enantiomers, make sure to draw the right enantiomer.
yeah. I think I probably could use more work with that or practice.
Yeah. That's why what is in A is the foundational class for like these series, what B and C, because that talks about stereochemistry, acid base reactions, nomenclature, bond line form, and then this is when we start learning about like the actual parts of the reactions, mechanism, synthesis, spectroscopy, uh,
Mm-hmm.
like syn addition, anti addition, Markovnikov, anti Markovnikov. That.
Yeah.
Okay, okay, that's good. Yay.
Yay. Thanks for giving me that one. That one was actually not bad because, like, I know we've only ever worked on like six-membered rings.
Mm-hmm.
So the five-membered ring, it was kind of having me think, is a five-membered ring possible? So then
Mm-hmm.
I was like,
Yeah.
yeah, let me just see.
Right. And then there's gonna be some reactions where you have to choose between the 5 and 6 membered ring. What would you choose, like based on what you know so far?
Six,
6,
because
yes.
I think five, there's a ring strain.
Uh,
Or,
not a big ring strain, but a little bit more than 6. Right, 5 and 6 they barely have ring strain, but 6 is more stable because well there's no ring strain for 5 and 6, but 6 is more stable because they're have the more preferred bond angle. You could say more preferred bond angle.
okay.
Or you can think of it as 5 has more ring strain than 6, but it's barely a big thing because even if you have a 5 membered ring right here, it's still stable enough to have no reaction with H2 PDC,
Right.
right? It won't break open the ring. But the very unstable rings would be the cyclopropane and cyclobutane like that, which would
Mm-hmm.
crack open under H2 PDC.
Right.
H2 PDC like that. But this cyclopentane or cyclohexane would not open up.
Mm,
That's good. That's good.
makes sense.
Yeah. Okay. Let me
Thank
see.
you.
Yeah, of course. Download Jenna's quiz 1 version A. Email it. Mm, oh, failed to. Oh, there you go. Okay. Oh. Okay. Okay. This is the quiz this Friday. A lot of vocabulary for Levens.
Yeah.
A lot of conceptual stuff. Were there any problems that you wanted help with specifically that you started?
Maybe we can start with 1A. I feel like I was able to do the rest, but For A, she showed the cis and trans products,
Mm,
and
yes,
I feel like I kind of struggle with drawing those out.
cis and trans products. Yes. Okay. So this is an alcohol reaction with H2SO4 and heat. So there's going to be 3 different types of alcohols that you could have: primary, secondary, and tertiary. And if you react this with H2SO4, it depends on what temperature you react this with. I think Leibniz gives you 135 degrees and 180 degrees as your two
Yeah.
choices.
Mhm.
180 would be the high temp, 135 would be the low temp. If you react a primary alcohol with H2SO4 and 135 degrees Celsius, well, before that, when we learned about SN2, SN1, E1, and E2 reactions, we know that SN1 and E1 reactions go together. They happen at the same time. SN1 and E1 reactions happen simultaneously at the same time. And in normal conditions, SN1 is major. It's going to give the major product. Unless heat is added. If heat is added, then the E1 product is the major product, right? So the S reactions like SN1, SN2 are substitution reactions. So we're just substituting the leaving group with the nucleophile. The E reactions like E1, E2, those elimination reactions, those are going to form double bonds, alkenes, right?
Mhm.
So think of the high temperature here as 180 degrees Celsius for Leibniz class. If you see this, then you know that your major product is going to be some sort of alkene, some sort of double bond, because we have heat, which was going to favor the E1 product or elimination reaction, right? So a primary alcohol is in 135 degrees Celsius, it's going to do SN2 reaction. For 180 degrees, it's going to do E2 reaction. For secondary and tertiary alcohols, they're going to do SN1 reaction in 135 degrees Celsius and E1 reaction in 180 degrees Celsius, right? So the first thing we have to do for this type of problem is to analyze what kind of alcohol we have here. What alcohol would you say we have here? Primary, secondary, or tertiary?
Secondary or
Secondary, right? Tertiary, because
Yeah.
how many other carbons is this carbon here attached to?
through
Mhm.
3. Yeah.
Yes, 3. 1 here, 2 here, and 3 here. So because this carbon here is attached to 3 other carbons, this is considered a tertiary alcohol. So we're going to worry about this row here.
Mhm.
Now we have H2SO4 in 180 degrees Celsius, which means that we're going to worry about this column here. That gives us this E1 reaction here for this reaction.
Yeah.
Right. But in all of the SN2, SN1, E1, E2 reactions, all of those reactions, their commonality is that they all require a good leaving group. Right now, we have no good leaving groups present here. Right, this alcohol is a bad leaving group for now. Right. Consider this OH as a bad leaving group.
Mhm.
But you notice how we have a strong acid here, sulfuric acid.
Yeah.
That strong acid is going to protonate this alcohol right here. Yes. And I'm going to draw it like this, the H2SO4 like this, where this oxygen here is going to use one of its pairs of electrons to go and attack or grab that hydrogen of the acid. And that bond between the hydrogen and oxygen is going to break and go onto that oxygen right there, kicking out an HSO4 minus conjugate base.
Okay.
Right. And when we do that, we are going to have this intermediate as a result. Right. This OH here is now an OH2 with 3 bonds, and before it had 2 pairs of electrons, 1, 2, but now it only has 1 pair of electron because it used 1 pair of electrons to make this new bond right here. This new bond between the oxygen and hydrogen has 2 electrons, and those 2 electrons used to be a pair of electrons on oxygen right there. Right. This is the new hydrogen right here, which is coming from that H2SO4 right there.
Yeah.
Okay. Now, what would be the formal charge of this group here?
Actually, formal charge was one of those things that I struggled with in A, so
Yeah, so let me go over that with you really quick.
okay.
Formal charge. There's an equation that you use, and it has something to do with divide by 2, but I don't use that equation as much because it kind of confuses me, and I have to like think more about it, right? But this is what I do. I think about formal charge is equal to how many. This is not gonna be accurate in the textbook terms, but this is what I think about when I do it, and then you get the answer, right? Like in my terms, but the textbook does it a different way, and it's more like specific. How many electrons an atom wants, and this is gonna be based on their group on the periodic table. And I'll give you examples of this so that you're confident on how to calculate formal charge, because calculating formal charge is a very important skill for mechanisms, right? Once you learn more reactions, you have to know like the skill of calculating formal charges.
Yeah.
Right? And think of it as how many electrons an atom wants, and we know that by looking at the periodic table and look at what group they're on the periodic table, minus how many electrons the atom has to itself. So giving some examples, right, which would make it more sense, let's look at this molecule here. Okay, let me see here. Let me make this clear. Okay, so we know carbon with a neutral bond is going to have 4 bonds to fulfill the octet row. So let's look at this carbon here specifically. If we look at the periodic table, carbon is on the 4th group, the 4th column of the periodic table. That means that carbon wants to have 4 electrons to itself. So the formal charge of this carbon right here is going to be 4 minus how many electrons it has to itself. Do you know how many electrons are in a single bond like that?
Can you say that again? You cut out.
Yeah. Do you know how many electrons are in this bond right here?
This bond, 2.
Yeah, 2. So each bond will have 2 electrons. 1 electron belonging to this hydrogen, the other electron belonging to that carbon right there, right? Because it's shared. Think of it as like 1 electron belonging to the carbon and the other electron belonging to the hydrogen right there. So this carbon here has 1, 2, 3, 4 electrons to itself.
Yeah.
So 4
Minus.
minus 4,
Yeah.
0. That's why this is a neutral charge right there, right?
Okay.
But when you think about pairs of electrons, all those electrons belong to that atom right there, because there's no other atom like sharing these set of electrons like that.
Yeah.
Right. So the oxygen is on the 6th column of the periodic table, so it wants 6 electrons. How many electrons do you see that this oxygen has to itself right now?
4.
1,
Or
2,
count-
3, 4, and there's more here because those are
Okay,
the,
yeah. So 6. We count
Yes.
the bonds too, yeah.
Yeah, you count the bonds as 1 because the other electron belongs to this carbon right here.
Mm-hmm.
So 6 minus 6 is 0, which gives this oxygen a neutral charge.
Yeah.
And in most examples of compounds, they won't show you the pairs of electrons. They are gonna make it implied, invisible, and you have to know how many pairs of electrons are there based on the charge. But they will give you the charge though. Like they either have to give you the charge or the pairs of electrons. In this case, since they're not giving you the pairs of electrons, you assume that this is neutral, and because it's neutral, we know it has 6 electrons to itself. 1, 2. So that means it has 1, 2, 3, 4 more out like that.
Yeah.
Right. Okay. Now let's look at this oxygen right here. What would be the formal charge of this oxygen here?
Would it also be neutral?
Yes, it would also be neutral. That's correct. What about this oxygen right here?
That has, so we have 1, 2, 3, 4, 5, 6, 7. So it would be a +1 charge or minus.
Yeah, 6 minus 7, -1, negative charge. Yeah, because the first number in the equation here is how many electrons they want to itself based on the group it's on
Yeah.
the periodic table. So it's -1 charge here for this oxygen. Nice.
Okay.
This carbon?
That one. 1, 2, 6. -2.
-2. So how many electrons does this carbon want to itself based on the periodic table?
4.
4, yes. And how many electrons does this carbon have to itself right now?
1, 2.
Oh, I see. 1, 2, 3, 4, 5. So yeah. Right now, as it's drawn, it's -2. But that's not very common. So let me just erase that hydrogen right there. Let me draw a more common thing that you're gonna see. Okay, what about now?
Okay, 1, 2, 3, 4, 5. So -1 charge?
Yes, -1. Correct. So this carbon here with 3 bonds and a pair of electrons, it's a negative charge like that. But you were right before. If it had 2 hydrogens, that is gonna be -2 charge, but that's not possible. Right? Can you think of a reason why it's not possible? Like, how many electrons does this carbon have if it has 3 bonds and 1 pair? Oh, I mean 4 bonds and a pair of electrons.
Wait, say that again?
Yeah. Why is this not possible here? Why is this not possible where the carbon has 4 bonds and 1 pair of electrons?
Oh,
Think back to Gen Chem.
carbon can't have 5.
Bond 5 pairs of electrons. It can have 10 electrons.
It
Right?
can't.
Yeah,
Oh,
because
okay.
it's 2, 4, 6, 8, 10 electrons. That breaks the octet rule.
Oh, okay.
Yeah, that's why this is impossible. But this is possible because that's 2, 4, 6, 8 electrons. That satisfies like the octet rule, but it will have a -1 charge.
Yeah.
Okay, what about this nitrogen here?
Nitrogen is where is it on the periodic table again?
The 5th column.
So it wants 5.
Yes.
And that's bonded to 1, 2, 3, 4. Neutral.
Yes,
right?
neutral. 1, 2, and there's a bond here.
Yeah.
3, 4, 5. 5 minus 5, 0. Neutral. Nice. Let's do 2 more here. This nitrogen here.
1, 2, 3, 4, 5, 6. So -1 charge.
Yep, -1 charge. Nice. Now last one here. This carbon here has no hydrogens. There's no invisible hydrogen on this carbon.
So +1 charge.
Yes. 4 minus 3 +1 charge. And there's a specific name for this carbon with a positive charge.
Carbocation.
Carbocation. Yes. You got it. Now let's go back to this problem. What would be the formal charge of this oxygen here?
1, 2, 3, 4, 5 +1 charge.
Yes, +1 charge, like that. So we have to draw out that plus charge in mechanism problems like that. Right. Now we don't stop here because we want to get rid of that positive charge. And to get rid of that positive charge, we want to get rid of this hydrogen here and give this oxygen a pair of electrons, right? Because that would give that oxygen 6 electrons now. 1, 2, 3, 4, 5, 6, right? So to do that, we have to bring in Oh wait, actually, no. That's something else. Forget what I just said. Like that. Because when we do that, right? Like when we bring in SO4 minus, grab that hydrogen right there, and then this bond between the hydrogen and oxygen, those two electrons are gonna go into the oxygen right there, right? That's how we neutralize it. But that's gonna go back to what we started with right here.
Oh,
So we don't want that to happen because that's gonna go backwards.
oh, okay.
Right. In other reactions, we want to do that. Like when we add the nucleophile in, we want to deprotonate the positive charge to get the new product. But when we do this, we won't get a new product. We get the same old product, same old reactant.
Oh, okay.
Okay. But because this is now positively charged, this group here, the OH2 plus, is an oxonium ion, and this right here is considered a good leaving group. Right. And we said that this is going to do an E1 reaction based on the conditions, tertiary alcohol, H2SO4, 180 degrees E1. And in all SN1 E1 reactions, do you remember what the very first step is? Like once we have the good leaving group for SN1 E1 reaction? Something to do with the leaving group. The leaving group will just...
It will just leave.
Yeah, it will just leave. So
Yeah.
this bond right here holding the leaving group just pops off like that.
Yeah.
Picks out the leaving group. And when we do that, this carbon here will have 3 bonds. And what charge would this carbon have now? What form of charge?
+1, so it would be a carbocation.
Right. And that's why I am getting rid of that wedge stereochemistry, because it's sp2 hybridized, which is flat and planar. There's no wedges, no dashes on that carbon. Right. So now, since this is E1, I'm going to do it Leibniz's way. She calls this the carbocation carbon. And these right here are the alpha carbons, the first carbon away from that carbocation.
Yeah.
Right. I'm going to draw out 1 alpha hydrogen for each alpha carbon. So all of these blue hydrogens here in blue are the alpha hydrogens. We have to choose the most stable one, most substituted one to use to make the more substituted alkene. And which one would that be? Let's say this is A, this is B, this is C.
B?
Yeah, B, because that's the most substituted one.
Yeah.
But before I make the alkene, I want to show you this concept here. This is a single bond, which can do free rotation. Right. And when I rotate that, I'm going to keep everything on the left side the same. And I'm just going to rotate this methyl group and methyl group right there. Right. So if I want to, like, let's say, differentiate these two right here, this methyl group here is now going to be down here. Right. So what I did was I swapped these two groups together. This flat methyl group here is this flat methyl group up there now. Right. I'm just switching these two places together. And when I switch that, this dash is going to become a wedge like that because I'm flipping it around. Right.
But how would we, is it always that when you rotate it, it's just gonna change the stereochemistry?
Yes, it's always going to change the stereochemistry from a
Okay.
dash to a wedge, or if there's a wedge, it would be to a dash.
Okay.
When we rotate it, it has to flip stereochemistry because, well, for this case, it does not matter because this is not a chiral center.
Yeah.
Right, so we don't put stereochemistry for non-chiral centers. But let's say this was an isopropyl group, then it would matter. Right, and the reason why is because if you assign R and S for that chiral center, and you flip it, you would also have to flip the stereochemistry to maintain the same chiral center. Like let's say this is R, and when you flip it, we want to keep that R to keep this structure the same, identical. Right, and to do that, we have to switch the stereochemistry from dash to wedge. Right.
Wait, could you explain the isopropyl part again?
Yeah. So if this was an isopropyl right here, right? Let's assign R and S. Do you remember how we assigned R and S from 118A?
I 118A was like, there wasn't anything for no guidance for me because like everything was kind of just thrown at me and I was expected to like
to learn
how to
everything by
do
yourself.
everything. Yeah. So like a lot of the stuff I know, but when I actually have to like apply it, it gets hard.
Oh, it gets hard, right? I see.
Yeah.
Let me see here. Oh wait, actually, I'll go over that with you, like how to assign R&S, but in the tomorrow session because it's coming to an end here. But this right here is actually an ethyl group. I forgot to add that group right there, but that's actually an ethyl right here.
Yeah. Okay.
So now we would have to include stereochemistry because this is a chiral center now.
Uh-huh.
But later on when we go over chiral centers, let's say this is R. I don't know yet, but I'll just say it's R right now, right? If I rotate this single bond right here, I'm just gonna switch this ethyl group and methyl group around. So the ethyl group is now on top, the methyl group is now on bottom, right? If I do that, if I kept this as a dash, that would switch or invert the stereochemistry to an S.
Oh, okay. Okay, I see what you mean now.
Right, and these right here would be diastereomers of each other, or like they will not be identical. Like if there was another cross center, they would diastereomers. But these would actually be enantiomers, right? R to S, like that, not identical molecules.
They're enantiomers in this case right now, but if it was wedged, then it would be diastereomers, right?
If it was wedge like this right here, it would be
Sorry, I mean
identical.
dashed.
Dash, like
Change that to dashed.
if it was dash right here, then these would be enantiomers.
Oh, okay.
Right, because there's only one chiral center, and that one chiral center would change, making it enantiomers. But right now, this is identical. This right here is the exact same thing as this molecule.
Oh, okay. That makes
It's the
sense.
exact same thing because it will have this exact same chiral center.
Yeah,
Right?
okay.
It's just rotated. Like this bond here is just rotated, but it's the exact same thing. Exact
Yeah.
same molecule. Right. Now, we said earlier that this is the hydrogen we're interested in because that's the most substituted one. So now we can bring in the HSO4 minus as a base, grab that hydrogen, the bond right there makes a double bond like that to form this alkene. Or if we grabbed this hydrogen on before we rotated the molecule, make a double bond there, we can get this alkene, right? Where this would be the Z alkene, this would be the E alkene. Do you know how to determine the differences between them, E and Z alkene?
I just know that Z is for cis alkenes and E is for trans alkenes.
Yeah, so it's very similar to that, but don't think of it like that because cis and trans alkene, they only work if the alkene has exactly 2 substituents.
Oh,
Exactly 2. But this alkene here has 4 substituents. 1, 2, 3, 4. 1, 2, 3, 4. So E and Z can work with multiple substituents, but cis and trans can only work with exactly 2 substituents. Right. So the way to think about it is make a line through the double bond like that. Right? Like wherever the double bond is, just make a line through that double bond.
yeah.
Focus on one carbon at a time. Let's focus on this left carbon right here. This left carbon right here, what would you say is the higher priority group? It's okay if you forgot, but what would you say, this ethyl group or methyl group?
It would be the ethyl group, right?
Yes, correct. That's a high priority group for this carbon here. Let's do the same for the opposite carbon. What would be the higher priority group? Oh, this group or this group right here?
The ethyl.
Yes, the ethyl. And notice how the 2 highest priority groups here are on the opposite side of the line. Like one is on this side of the line and the other one is on that side of the line.
Oh, okay.
That's why this is E, right? We ignore the lower priority groups and we focus on the 2 highest priority groups on the 2 different carbons.
What would happen if you look at the lower priority groups?
If you look at the lower priority groups, then you would get the wrong answer because let's say, well, actually, if you just like look at the lower priority groups here and here, then you would still get E.
Yeah, because they're both each
Yeah.
One is on opposite sides.
Right.
But that not always the case.
That would always be the case if the highest priority groups are on opposite sides, but that's not how we like usually do it or teach it.
Okay.
So yeah, you could do that as well. That would work as well.
Okay.
Right? But make sure if you do the lowest priority group, you do it for both carbons because if you do one higher priority group and then the other one low priority group, then you would get the wrong answer.
Oh,
right? You
yeah.
get Z, but that's not correct.
Okay.
Right.
So we shouldn't think of cis and trans for E and Z.
Yes, do not think about that because E and Z is going to work with more than 2 substituents. Right? Cis and trans, they only work with 2 substituents. This is cis, this is trans, and we could say that because there's exactly 2. 1, 2, 1, 2.
Yeah.
Right.
Okay.
But if you have something like this, we cannot say cis or trans because there's 3 substituents now.
Yeah, that was I was wondering about that because I was looking at more complicated alkenes and I was like, how would we tell if it's cis or trans or E or Z if you can't really tell if they're symmetrical or not.
Yeah, you can't really tell if it's symmetrical because if it was symmetrical, which I will give you after this problem,
Mhm.
let's see which one's the E and Z alkene. What would you say is the E in Z alkene? Let's focus on this one. Is this E or Z here?
So if we draw a line,
Draw the line.
would it be? So on one side we have, on the bottom we have an ethyl, and then on the opposite side we have a methyl. So
Oh,
they-
wait. So if you're focusing on this carbon here, we only focus on one carbon at a time, right? Let's focus
Okay.
on this carbon here. Ignore everything on this side. Like, don't look at that side, right? So now we're going to compare this ethyl with this hydrogen here.
Oh, they're not the same.
Yeah, they're not the same. Which one would have higher priority?
The ethyl?
Yes, the ethyl. So I'm going to circle that ethyl right there. Right. Now we go on to the other carbon. Ignore everything on this side now.
Okay.
Right.
We have a methyl and an isopropyl. And would the isopropyl have more priority?
Yes.
Okay. Okay, and they're both on the same side, so that would be cis.
Yes, that would be cis. Oh no, we cannot say cis. Why
Yeah,
can't we
we
say
can't
cis?
say that. So it would Z.
Yes, and why can't we say cis?
Because there's more than two substituents.
Yes, and you can think of Z as the two groups are on the same side.
Yeah,
The
I was
same
thinking
side.
of that, yeah.
Yes, that's good. Now let's do the same for this one. We already found the priority groups, this ethyl and isopropyl, but what do you notice about those two priority groups now?
They're on opposite sides.
Which would make it?
Wait, hold on. I got lost. Wait, okay, so can we do the one carbon at a time again?
Yeah.
Looking at just the circles confused me. Like
Yeah.
searching both of them.
Right. Let's look at this carbon here. Ignore everything here. Don't look at that.
Yeah, okay.
What would have higher priority, ethyl or hydrogen?
The ethyl.
Yeah, that's why I'm circling that one. Now we ignore everything on this side and look at this carbon here. And we're going to compare this isopropyl and this methyl here.
Okay, yeah, and then the isopropyl.
Right, and then once we find our two highest priority groups, then we compare where they are at on the line.
Yeah, okay. I forgot that when I was looking at the bottom ethyl, I forgot that we had to look at the hydrogen on the opposite side of it.
Right, and that hydrogen is sneaky because it's invisible.
Yeah.
Yeah, right. Let me give you two more here, and then let's call it a session.
Okay.
Let's do this. Okay, let's do these two here. Yeah, that set, and let's do this set down here. Okay, let's focus on this one here. What would you do first?
Draw a line through the alkene.
Okay, yep.
And would we look at the ring first or the OCH3?
So you get to choose. Which carbon would you want to focus on first? This carbon or this carbon?
We can look at the second carbon.
This carbon right here?
Yeah.
Okay, so we're gonna ignore everything here. Okay, and if we look at here, we have to see which one has a higher priority group, the tert-butyl or OCH3 methoxy.
Is it the tert-butyl?
It looks like the higher priority because it looks bulkier, right?
Yeah.
But don't think about the size as priority, right?
Okay.
That was the trick that I wanted to trick you on this problem. Right? Because like lipids might trick you like that too.
Okay.
Even though it looks bulkier, like even if it's like this, right? This right here does not mean it's high priority. You have to look at the very first atom attached to the carbon. So what's the very first atom attached to that carbon in this group here?
Oxygen.
Yeah. What about this one?
Just another carbon.
Right. Which one has higher atomic number? That's the factor.
Oh, okay. Oxygen.
Yes, atomic number is the important thing here. That's the one that determines the stability. That's why this group here is higher atomic number, even though it's smaller, but that
Yeah.
size doesn't matter. It's the first atom's atomic number.
Yeah. Okay.
First atom's atomic number. There's more tricky concepts of practice problems as well, but I want to show this to you tomorrow. But for now, let's just end up with these four. There's a lot I want to show you.
Okay.
Yeah. Okay. Let's look at this one now. Ignore this side. Now let's compare this carbon and this hydrogen here.
The I don't hydrogen is always the lowest priority, right?
Yes, hydrogen has atomic number of 1. Carbon would have atomic number of, I think, 12. Yeah, 12.
Oh yeah, we have to look at the carbon. So yeah, the ring would have more
Mm-hmm.
priority.
Yes. Mm-hmm. Now, what would this look like here?
Z.
Yes, correct. And this one here, what would you say this one is, and how would you explain how you got there?
Okay, let's see. I say E because if you draw a line, then you'll see that it's the ring and then the OCH3.
Mm-hmm. The
Which
ring has priority over H. OCH3 has priority over this. Let's keep it the same as last one. This bulky group right here, and they would be opposite from each other, making an E. You got it. Nice.
Nice.
Mm-hmm. Okay. Let's look at this one here. This one's tricky.
Yeah.
This one, well, first let's focus on this carbon here. If we focus on this sulfur versus this hydrogen, which one would you say is higher priority?
The sulfur.
Yes. So this group at the bottom carbon is the higher priority group, but this carbon here, same atomic number.
Yeah.
If there's a tie, then you look at what is attached to this carbon, ignoring the bond previously. So this carbon here at the right is attached to 2 carbons and 1 hydrogen, right? 2 carbons, 1 hydrogen. Same as for this one here, 2 carbons, 1 hydrogen. So they're basically attached to the same group, right?
Yeah.
And you notice how these are the same groups?
Yeah.
Can we assign which one's a higher priority, or are they the same?
They're the same.
They're the same, so we cannot assign E or Z here. No E or Z.
Oh, okay.
Same as for this one, right? Actually, since we're on that topic already, I want to just show you this anyway.
Okay.
Like this. Okay, this one right here, like this. Okay. How would you find E and Z for this one?
So for the first carbon at the bottom, the OH would have priority over the hydrogen. And then for the second one, you have an isopropyl that would have more priority.
This one here?
Yeah.
Yeah. So this isopropyl here, if we compare it to this tert-butyl, this carbon is the same atomic number as that carbon. Then we see what is attached to this carbon here. This carbon is attached to 2 carbons and 1 hydrogen. 1, 2, 1 hydrogen. This carbon here is attached to 3 carbons. 1, 2, 3.
Mm-hmm.
Okay. So we could cross out the 2 carbons because they match. But now, which one would have higher priority? C or H?
Wait, where did the third? Oh, because of the methyl groups. Oh, then it would be the tert-butyl because
Yes.
there's more carbons.
There's more carbons, right? So if there's a tie, then you see what is attached to the tie, and then you make them go against each other.
Okay.
This here had only 2 carbons and 1 invisible hydrogen, whereas this carbon here has 3 carbons, 1, 2, 3, which beats the the team over here.
Mm-hmm.
So if there's a tie, that's the other one I wanted to go over with you. Like you look at what's attached to that tie.
Yeah, so then this would be E.
Yes, you got it. Mhm. Nice. Yeah.
Yay.
Uh-huh. What time's your quiz this Friday?
It's at 8 a.m.
8 a.m. Oh, that's so early.
I know.
Yeah. Oh my God.
This is my second quarter in a row having OChem at 8 a.m.
Oh my God. Wei had 8 a.m. class as well.
Yeah, yeah.
That's crazy.
Um, thank
How
you.
did you
Huh?
hear about me? Like again, like how did you find out about me?
Um, I went to your final review session, but I forgot who told me about it. I just knew that there was something going on finals week,
Right.
and I went to that, and then my friend told me that you had a YouTube channel. So I
Uh-huh.
went on that, and then I don't know, I just like did a deep dive and found your website.
The link tree and all the
Yeah, the
links.
link tree, yeah.
Oh my God.
Yeah.
Oh my gosh.
That was such a lifesaver because like I found out about you literally the week before finals. So I was like,
Mhm.
I need to visit your office hours this quarter.
Yeah, that's so good, and I'm so happy to see you here, Jenna.
Thank you.
Yes, you're
This is
second
really
year.
helpful. What was that?
Are you a second year this year?
No, I'm a third year.
Oh, you're a third year. I see. I see. Yeah. What's
Yeah.
your major?
I'm MPB, but I'm thinking of switching out.
Oh, I see. I see. Yeah. Yeah.
Yeah.
Yeah. People take their own times, Uh-huh.
Yeah. Do
Right. Oh,
you by any chance know if there's any like resources on campus for like NPE classes?
oh, NPB classes like tutoring.
Yeah.
AATC. I don't think they have NPB tutoring for drop-in.
Yeah. Yeah, they don't.
Yeah. They might have one-on-one tutoring for that class, like through the website, but I'm not too sure on like the tutoring for those classes.
Okay.
Yeah.
Because I'm taking 110B this quarter and it's a lot of physics and I've never taken physics before, so it's
Oh, like the
really
physics
hard.
series? Oh
Yeah.
no.
Yeah.
Yeah. Dang. Physics, I don't like physics at all. It's very tough. It's very annoying.
Yeah. It just looking at it is so intimidating.
Yeah, like I like did not enjoy that at all, and especially at Davis. Like I don't know if you heard, but the physics department here at Davis, the way they teach it is not very organized, not very good, and like there were like petitions all the time, trying to change
Really?
it. Yeah, it's
I
crazy.
heard it was bad, but not like not like that.
Yeah, it is. It is.
I heard that they structured it in a way where like you can only get a C. Like the curve is so bad that like everybody just gets a C in the
Oh
class.
my God. Yeah,
Yeah.
that's not good.
Yeah.
Right. I'm curious, who was like did your friend that told you about my office hours or like the final review session? Did they attend my office hours frequently or no? Or they just showed up to the final review session?
No, I don't think they've ever gone to your office hours, but
Uh-huh. Oh, but they know about the review session. I see. That makes
yeah,
sense.
we both went to the review session together.
Mm-hmm.
Um, I think before that, she found your YouTube channel, and
Ah.
instead of watching Way's lectures, she was just watching your YouTube videos.
Oh my God. But my YouTube
Yeah,
videos, like they're based on the students' questions here. So like I
yeah,
did not go over everything in lecture because it was just based on the students' questions. But I had some way people asking questions about her class. So she probably benefited from those questions and me going over those questions and
yeah,
problems. Uh,
yeah. It is helpful hearing other students because like they're asking questions about the same professors that we have.
uh-huh.
So yeah, that
Right.
was
Yeah.
better than trying to figure out um what to learn on like through other YouTube channels.
Yeah, right. And
Yeah.
I'm curious, are you down for like private tutoring sessions? I can give you a trial session if you're interested, but if not, you can just go show to these office hours.
Um I think maybe I'll try a couple more office hours and see like how often I would need them and if I feel like because right now it's pretty much review from 118A. I feel like it kind of put me ahead, but
Yeah,
maybe later on it's gonna get harder and I'm gonna be introduced to like newer topics that I've never really heard about.
definitely, because there's 118C topics in 8B as well. But
Oh,
you don't have to worry about NMR anymore, like no spectroscopy, no IR, so
yeah, I
good.
heard. Would you be able to do lab help? Because I feel like I'm struggling in lab
Hmm.
kind of.
I have the pre post labs for the 118 series, A, B, C. I could ask around for the 8B labs, but I could try helping out for lab as well. But just send me the labs ahead of time,
Yeah.
and then I could help out with that. And
Okay.
go look through that. Yeah,
Yeah. Okay.
yeah.
Yeah, I'll just see like how office hours are going with me for now.
Mhm.
But I will definitely let you know if I'm interested in the private tutoring.
Yeah. Okay. Yeah. That'll be great. And there's
Yeah.
also final review sessions this quarter at the end of the quarter. So
Yeah.
I want to see you there too.
Yeah, no, I'll definitely show up.
Yeah.
Thank you so much.
Yeah. No worries, Jenna. Good night.
Well, you too. Good night.
Yeah. See ya.
Bye.
Bye.